Let's start the second session, second paper session of these LAC. We're going to have 4 papers, and we'll try to keep to schedule as much as possible. So we're going to start with Dr. Lan Fan, who is going to be talking about Audio, and so the floor is yours.
Thank you. Hello. Yeah. Thank you, everybody, to be here. Yep, I'm Lam from the Austrian Institute of Technology, AIT, Austria. And it's really nice to be here to present our work and share with the audio community today. And yeah, very thank you. And hope you enjoy lunch and enjoy my presentation. Yep, and our works actually I'm belonging to the design team, data scientist and intelligent technologies team in the centers of safety and security. So that's the reason why our work focus on some application related to the security. Yep, and we focus on in this work we focus on audio and create something. Some application which mainly focus on analyzing audio and likely audio exploration and audio content. For example, this is a sound scene, the sound events inside the audio, and human speech inside the audio, and the content inside the audio is not likely the music or the emotion. Also have the emotion and defects inside. Yep. Okay, let's go into the detail. Firstly, wait some second. Okay, yeah. Yes, agendas. It includes 3 sections: proposed system, system deployment, and experience reserve and conclusion. The first one is for the proposed system. Can you see here? The proposed system, our proposed system comprises 3 main components. The first one is we develop the user interface, where the user can interact with the tool. The user sends audio file. Yep, and after that, the tool will analyze audio. Yep, and create a JSON file, model reserve, that's a JSON file. So for each model, we have the one JSON file. And after that, the only JSON file will integrate into one JSON file that is standardized, create the one JSON file, and that is the audio analysis phase. Yeah, and the final component, that's the audio retrieval phase. In this component, we make use of large language model to create the interface between the user and the JSON file. And the user can just to ask the contents, retrieve the content, the audio content inside. Yep, and for the user interface, that's it. We use a Streamlit, very simple and easy to approach. And the second one, that's the audio analysis file. Okay, so we integrate the multimodal inside here. Maybe you know the Whisper model from the OpenAI. That's it for speech to text. Yep, and language detection. And Bar model to English translation, because a Whisper can detect German and French, some language, and we transfer into the English. Yep, and PANN, that's the acoustic event detection. For example, the knocking, the cat sound, the dog sound, the sound events inside the audio. And the note is the speaker count and some other model, yeah. The speed brain, way to vex, and keys for audio captioning, yeah. And a lot of model, and we use the model with the MIT license and a Pico license, so that is easy to integrate the new model, and we can remove the model, we can integrate the new model with the MIT and Apical license. It's a very flexible to integrate the new audio model. And we also develop 2 models, that is the acoustic sync classification and the defect detection. Yes, that is our model. And for two model that we develop, we add the link for the 2 journal published. Yeah. And for and the outputs of this component will create the decision file with the metadata. For example, we know the file name, the duration, sample rate, and we have the acoustic information, we have the human speed information, we have the language detection and defect detection. A lot of metadata with the reserve stored in one JSON file. This is standard JSON file. I mean, there's a lot of model. We have the many model and one model, one JSON file, and we integrate our own JSON file into one JSON file. We call the standard JSON file. And the final component that is the audio retrieval phase. Yep. And in this component, we develop we make use the large language model to interact with the JSON file and the user, between the user and the JSON file. And we use we try two types of the prompt engineers, COT and zero source prompt engineer. And currently we use the llama model, a billion parameter. For this version, the work I present today, that's it, a billion, but we are working on and explore the small llama model and other small model to explore whether we don't need the large language model, which is a small model, and tries whether we can optimize and improve the speech of the system with the smaller model. And the system deployment, yeah. And you can see here, we have the first, that's it, the flowchart. The flowchart shows how the audio is processed inside the tune. With the three flow, that's a sound-based task, speech-based task, and the final is for the captioning, yeah. I will not go into the detail because everything will describe in the paper is very detailed, so we just introduce, because for the flowchart we separate the tasks into three groups, yep, sound-based and speech-based and the audio, yeah. And here, the way we deploy it, on the AWS server, we create for three flow we create the one Docker image, yeah, and totally we have the 3 Docker image for audio for 3 groups of audio tasks. We also have one Docker for I mean that we have the 3 Docker for 3 group of audio tasks, and we have the one Docker for the base. I mean that's the base Docker because the 3 Docker use a GPU. Yep. So to create and deploy on the AWS, we first create the base Docker image, and 3 Docker image used for the audio will reuse the base Docker image. The base Docker image will integrate the license, not license, the driver and everything that can run on the CUDA driver with the GPU. And the experimental reserve, yep. And that's the slide just represent the way represent the reserve. That's the experiment that I put the audio into the server, and after that I charge with the tune and get the reserve. And we try with the 2 prompt engineer, and we try with different question, and some question is out of the topic, and some question is the tool can explore and retrieve information from the audio. Actually, currently we still working on the prompt engineers, and we also trying the fine tuning with the small model to make sure that the large language model answer the right question and not answer the question out of the topic. And we try a lot of experiment to make sure that the user can interact and get the correct information and not our topic. And finally, there's a conclusion. Yep, with this approach, we can integrate the multi-audio task and the purpose. Yeah, because all the model use MIT and Apica 2 license, so we can remove the model if we have the better model. Yeah. And we easy to integrate. If we compare this approach with the audio large language model, maybe there is a pros and cons. Yeah, for the audio large language model, it's just for general purpose. And if they need to add another task or maybe the new task, they have to retrain again, and it takes a lot of time and take a lot of resource. But with this approach, okay, maybe it's not, it's likely we use a multiple model, but it's easy to integrate and update. Yeah, and if we focus on specific application, for example, in our case, that is for security, it should be approach this way. It's easier and flexible to integrate. That's also the highly adapt and integration and modification. And we use a large language model to create a friendly user interface to interact with the tool. Okay, thank you for listening. And for the demo, actually, where's my cursor? How can I? Yep. Oh, sorry. Is it here? Is it here? Yep. Yeah. Oh. Yeah. Maybe it's more, but you can see the IP address here. Actually, we open this IP on the Amazon Web Service, and you can copy this IP address and try it on your computer. I will open maybe someday in the conference, and after that we turn off because we are still developing. Yep, and you can try with this IP address. You can push your audio, and after you follow the guide on the left hand side, and after that you can ask some question. Maybe it's good, maybe it's not good, but just try and enjoy. That's everything I want to say. Thank you very much.
Thank you very much. So, are there any questions from the audience? So I'll start with something. So this works runs as a web service from Amazon, from the Amazon server.
Yeah, actually, sorry, thank you. Actually, we can deploy any on any infrastructure that we want. Yeah, the AWS just because maybe something is difficult to explain because maybe some related to some security in our center and our company. So firstly, we develop on the AWS, but after that, when we have the final version or maybe official version, we have to move to the server in my company. Yep, and I don't think the infrastructure is a problem because if we can use a Docker image and we can use the Docker image with the base Docker image with the CUDA driver, okay, we can deploy any infrastructure that you want. Okay, if your infrastructure have the GPU, CPU, okay, we can build, yeah.
Yeah, so it's deployed under kind of a Linux environment.
Yeah.
By normally, is that what you say? Yeah.
Yeah.
And then you have the web interface to talk to it. You always have this web interface here to
yes, that's the web interface here. This is running on AWS. Yeah.
Yeah. Okay.
The current IPs are on AWS. Yeah.
Okay. Thank you. Anyone else? Okay.
One of your slides showed you use the LLM Llama 8B. How many languages does it currently support?
It depends on the language. You mean the human speech inside the audio recording? Yeah? It depends on the Whisper model. Yeah.
Oh, okay.
I use the Whisper model to translate speech to text, and maybe the Whisper model supports a lot of language. But actually, I tried some experiment and I found that Whisper model is good for EU language rather than the other language. For example, it also supports the Vietnamese language as in my home country, but it's not good. Sorry to say that's okay, because maybe the lack of the data, the training data, and maybe the accent is very different. Completely not good.
Any other questions? Another one.
Hi, thank you for the talk. Can you elaborate a little bit about the use case, like what the company you work for, what
Okay.
would they use the software for?
Um, okay, maybe someone here knows, maybe not knows about the EU project called the Starlight. The Starlight, that's the EU funding projects. That's a company also involved. Yeah, and in this project, people raise some tool for the police, Europol to use. Yes, and the Europol needs some tool like image analysis and the audio analysis, speakerization, something like that. Yeah, and that's the reason why I want to share with you the use case as a company, my company work on. Yeah, and this is just a general application, not a specific application, but we can separate. Okay, we may focusing much focusing on human speech, for example. Okay, we don't need a lot of model. We just use okay whisper for speech to text, and maybe the speak to embedding to compare the embedding of the speaker with the criminal, something like that. A very specific use case. Yeah, yeah, just almost focus on the security domain. Yeah.
Any other questions? I think I heard a question, just someone speak, and I captured something there. Maybe we should ask. What's the license?
Yeah.
What's the software license? This is
The software license. I'm not sure about the software license. It depends on the company. Yeah, but with this paper is detailed very. Is in the paper is a very detailed and almost the tool used in the paper is the open source. Yeah. So, and maybe we don't open the license, but with the paper you can replicate very easy. Yes, very easy, because that's the open source. We just download and config, and after that you run. Maybe we need more time to make the tool run smoothly and speed up the tool, but basically everybody can replicate easy because it's not likely the hidden source code. Yeah.
There were some components that were developed at AIT, which is so.
Yeah, you're
what's
right.
the license for those?
Yeah, but you can also find and replace this module by another module with the open source. The open source is very easy because it's implemented on the PyTorch and easy for everybody to replace and then use the MIT and API license. Yeah.
Any further questions? Okay, thank you very much then.
Yeah, thank you for listening.
So do we have the next speaker? We can follow on. Patrick Lai. Yeah. So the next paper is by Patrick Lai, and it's Audio Reach, an end-to-end solution. So. No, I am under orders. Yeah. Okay. Right. Okay. The floor is yours.
Hello? Okay, so I guess everyone can hear me now. Okay. Hello, everyone. My name is Patrick Lai. I'm from Qualcomm audio software team, and I've been working on Linux audio since 2007. The first Android phones. I happened to participate in the original development. It is a pleasure to be here. This is the first time I attend the Linux audio conference. And today, I'm here to talk about Audio Reach end-to-end audio solutions from Qualcomm. Okay, so Audio Reach is an embedded audio solution developed in-house in Qualcomm, mainly starting with the, for Qualcomm SoCs, that has a dedicated audio subsystem that has, like, inside that audio subsystem, there's a dedicated DSP, hexagon DSPs. There's a lot of content in these slides, so I'm not going to go through these things in detail because it's covered in the later slides. But just having said that, Audio Reach is a solution that spans across host PCs and embedded device. Then it mainly consists of three major components. Starting from the bottom is the Audio Reach engine. Essentially, it's a signal processing framework. And we also have the Audio Reach drivers that's controlling the Audio Reach engines. And then in order for us to operate in different device sectors, which have their own ecosystems built up, we need to adapt Audio Reach solution to different platforms. So we developed the OS platform adaptations to work with Windows, with Androids and Linux, even QNX, and there's other proprietary OS as well. These three components mainly run on the embedded system. Then we also have Audio Reach Creator. That is the main tool that enables all the workflow for all the developers. Okay, and then the statement I'd like to make is Audio Reach is a proven solutions. As you can see that Audio Reach has been deployed onto a wide variety of products that Qualcomm has the market share in. And as you can see, it's a pretty wide range of devices or a type of products with a very different computings as well as memory capacities. So we believe that Audio Reach being able to deploy on all these devices is a proven solutions. Now, given that we believe Audio Reach is a proven solutions, then we believe that by contributing Audio Reach to the audio developer community, the developer of audio solution will be able to benefit from Qualcomm deliverables. So last year, we decided to open source Audio Reach. Today, you'll be able to find the project site on GitHub. There's also documentations. There's a pretty goofy promotion YouTube video. Feel free to check out. There's a lot of stuff about Audio Reach. Given the time, you can probably, if you want to learn more, come to the demo, as well as go check out the site. For this presentation, there's three main messages I'd like to give about the open source project. One is Qualcomm like to make sure this solution's ecosystem friendly. So we want to make sure that not only we can run Audio Reach on Qualcomm hardware, we also want to support a non-Qualcomm hardware. As a matter of fact, if you come to check out the demo later, I have a Raspberry Pi running. Even though Raspberry Pi doesn't have the DSP, the main purpose is more of showcase the features of Audio Reach on pretty cost-effective platforms and with wider broader community of developers developing on Raspberry Pi. We're also actively working on porting the Audio Reach onto a non-Qualcomm platform that's with SoC that has extends a DSP as inside their audio subsystems. Okay, so that's the first message. Second message is when we open source Audio Reach, we'd like to have a broader community developer able to use the Audio Reach solution on a both proprietary and open source products. Hence, we select the license type to be BSD3 cloth clear. Hopefully, people can make use of it even for a proprietary product. And then the last point I'd like to make is it is our hope to grow this open source project to be a community-based project. So we definitely welcome the community developer on board, contributing as well as providing feedback. We're willing to form a steering committee to help shape this open source project together. Okay, so now we kind of know a little bit about Audio Reach and the open source project. Now let me get into a little bit about what is this embedded audio SDK, the composition of it, and also some of the feature highlights. Before I kind of start going through the feature sets, I just want to point out that based on, as you can see in the color legends, not everything mentioned here is built out today. What I like to kind of express here is we have a roadmap to kind of build up this whole end-to-end solutions. And if you like these features, the roadmap, feel free to also join these bandwagons and start contributing. Okay, so as I kind of mentioned in the past, in the previous slides, Audio Reach is a solution that covers a span across the host PCs as well as embedded device or the SoCs. And especially on the SoC side, if you look at all the modern SoCs, this is not specific to Qualcomm, as many other third-party chip vendor also have such an architecture where you have a different subsystem. On the application side, you have application subsystem typically run ARM processors. And then on the same SoC, you also have dedicated audio subsystems with DSP for Qualcomm hardware. Then it's mainly hexagon DSPs. Then on some other SoCs, a lot of times they have Extensa DSPs. Then also on Qualcomm hardware, besides audio subsystem has the hexagon DSP, we also have many other general purpose or computing DSP for you to offload the computations if you need to. Okay, so now let's get into the Audio Reach SDK compositions. So the very first thing, starting from the embedded PC, is we have Audio Reach Creator. This is a one-stop tools providing the GUI environment for the use case designer to design use case by drag and drop different processing modules to form your use case graph. Along with with the use case graph, you'll be able to configure all the modules that is linked in your use case graph. Besides just offline designing your use case, during runtime, you can actually connect to the embedded device for the real-time, in the real-time calibration mode. In that mode, you'll be able to tune the modules by doing set params, get param, in order to kind of tune the audio processing modules at runtimes. And you'll be even able to do real-time audio graph modification. That means while the use case is running, you can actually add or delete audio processing modules in the use case graph without even stopping the use case. And then also being able to, besides just the tuning in the real-time mode, a developer will be able to see how, run the profilings in order to see how your audio processing modules, like the CPU cycles, run the profiling to learn about how much CPU cycles is taking, and as well as the memory it is taking. So that's one-stop audio tool to be able to do all these features. By the way, just to let you know today, Audio Reach Creator is not open source yet. We do make it freely available in Qualcomm Developer Network. In the project documentation side, we have instruction to kind of instruct a developer how to download the Audio Reach Creator. By the way, the name is not Audio Creator right now. It's called Qualcomm Audio Calibration Tool. But later on, we'll be open sourcing this and rebrand this Audio Reach Creator to Audio Reach Creators. Okay. Now you know about these tools. Let's come to the SoC side. So once the system integrator or the developer is able to design the use case, and you can actually save into the audio calibration database and push onto the device. And so that instantly, whatever you design in the Audio Reach Creator will get reflected on the target. So the next component is this OS agnostic graph services library, which know how to interface with the ACDB files to get all the use case configuration, and then interface with the Audio Reach engine, which is the signal processing framework, to send down the graph definition in order to construct the use case graph, and also be able to exchange audio data, the PCM data, and even compress offload, compress bit streams such as MP3, AACs with the Audio Reach engines. Then in order to adopt, as I mentioned, in order to adopt to different product that's running different OS platforms, we have, and a lot of the platforms, such as Linux, has a pretty established ecosystem software, such as ALSAs, Pipewire, Pulse Audio. So we we develop a plugin to plug into all this ecosystem software, so that we allowed application which was originally developed on top of these ecosystem APIs. They don't need to make a change in order to interact with Audio Reach. And then as I mentioned, Qualcomm's SoC has dedicated audio subsystems. We have basically Audio Reach engine running in a dedicated DSP on the audio subsystem as Audio Reach engine. It's a pretty comprehensive, flexible, and portable signal processing framework with a lot of plugin capability. Today, as algorithm developers, as long as you're able to wrap your algorithm processing library into a CAPI interface, then we can easily plug into the use case graph running on the Audio Reach engines. It also supports dynamic loading, so you don't really need to statically build with the Audio Reach engine in order to make use of your algorithm graph. So another key capability I'd like to highlight is, as you can see, Audio Reach engine is not just running in dedicated audio subsystems. Even on the application processor, we have enabled Audio Reach engine to run on the application processor, as well as the offloaded DSP. So the idea is, in order for you to, like as an algorithm designer, if your algorithm processing exceed the computing the capacity of audio subsystems, we have the Audio Reach has a solution allow you to partition your processing processing need across different cores. And those cores doesn't have to be the same type of cores. It can be heterogeneous in our case, you can run the computing on the hexagon DSP, hexagon architecture, while some of the processing can be running on ARM. Then, in order to realize our vision of developing an off-target environment and later on deploy onto a target, we have actually developed off-target simulation platforms, which we currently still use internally. Later on, we'll plan to open source it. Okay, so these are the things that exist for audio reach today. And now let me go through the things that we, in the future, would like to build. So in the future, we'd like to have tight integration with standard IDE, so that the developer will be able to, such as Visual Studio Code, so that the developer will be able to, debug their algorithms, at the same time run profiling about the algorithms in the off-target environment as well as on target, directly using the IDE. We also like to have a close integration with industry standard algorithm design tools such as MATLAB, so that developers who's already familiar with MATLAB doesn't really have to. It lowered the hurdle to work with audio reach by continuing to work in the MATLAB environment and easily port it onto audio reach. Then, as I mentioned, we have some off-target environment platform built. Eventually, we'd like to enable the end-to-end validation, even including the application as well as the ecosystem software such as Pulse Audio, Pipewire, and able to simulate this all in the off-target environment. Okay. This is envisioned workflow that is coming out of recent engagement Qualcomm has with MathWork. So the idea is we like to address two kind of algorithm developers. If you look at it from starting from the top, as I mentioned in the previous slides, for the independent software vendor, so the algorithm developer who's already familiar with the MATLAB, the idea is they can continue to work on, in MATLAB Simulink environment, develop their algos, run the simulation, validate with their test vectors, everything the same as the same workflow as before. And then, if their algorithm will require a lot of computation capacities, then the MathWork offers the system composers so that you'll be able to partition your algorithm across different cores. Then with Audio Reach plugin, which is what we are kind of currently engaged with MathWork on developing this Audio Reach plugin, then by end of when the developer is done with all their validation, simulation, optimizations in MathWork, MATLAB environment and System Composer environment, there will be a capability to export the net list, the use case net list from the System Composer, along with the metadata describing how the API of the algorithm modules into a metadata. And then you'll be able to import into Audio Reach Creator. So instantly you have your use case graph being converted into the Audio Reach graph definitions. Also, the module that you have designed will be able to instantly get imported into Audio Reach Creator, and then you can start using your algorithm modules to be used in the use case. And then on these directions, Qualcomm is actually has worked with MathWork to provide this hardware support package. So the idea is we'll be able to generate algorithm modules, compile for our hexagon DSP instructions, and it's already optimized, and at the same time CAPI wrap into with the CAPI interface, so that you can easily plug into the audio-rich engines. Then now you get into the off-target simulation platform using the audio-rich SDK, the off-target platforms. The vision is you'll be able to run natively or plug in the simulation from the chip vendors and simulate using the chip vendors simulators. And then once you're done with optimization, profiling, the tunings, then we want to be able to easily deploy onto a target, and then the same integration workflow as done on the off target, you can do it on the platforms. So that's today we have most of the pieces done at this stage as well as this stage, but there's as I mentioned, not everything has been built so far. So these are the things that we have on the roadmap. And then one thing I forgot to mention is we do have algorithm developer that we are working with. They develop their algorithm in C directly. So for that type of developers, they'll be able to import their modules directly onto the simulation platform, as I mentioned. Okay, so how is Audio Reach supported on Linux? So we actually offer 3 different options. The first option is the ALSA kernel drivers. We do recognize that the traditional Linux architecture has the drivers built into the kernel. So we have a set of ASA compliant driver upstream into the Linux kernel, but it only provides a very basic functionality to enable a class of developer who are accustomed to ALSA kernel stack. And then we also have option 2, which I call ALSA plugin. So this one adhere to the de facto user space, Linux user space architecture, which application at the client would call into the ALSA library APIs to interact with ALSA drivers. So we have the AudioReach ALSA plugins, which plug into the ALSA underneath the ALSA library. It can be the ALSA library as well as the tiny ALSA, so that it can intercept all those commands and then work with AudioReach natively to provide a much richer set of AudioReach features. Okay, and then we also have option 3. So if you think about nowadays, there's a lot of use cases that you can run on the phones, right? You can run audio playback at the same time having voice call. So, so we also provide this platform adaptation layer options for people that wants to run a pretty complex concurrent use cases that a lot of times require dynamic reconfiguration, such as if you plug in headsets, and then all of a sudden you have a Bluetooth with much different capabilities. All these are kind of all managed inside PAL. Okay. So what time is it now? Okay. So so I am running short of time, so I'm not going to go through AudioReach engine in detail. This slide, the main purpose of this slide is just to showcase a lot of features is supported by AudioReach engines, and is very friendly to algorithm developer because it support interlinking of algorithm designed for different frame size and media formats. So Yeah, so I'm going to skip the slides, but the point is audio-rich engine is a pretty feature-rich signal processing framework. Okay, so hopefully you guys have come to know more about audio-reach. So I just want to reiterate that we believe that open audio-reach can benefit the audio developer communities. I know I'm speaking in Linux Audio Conference, but this project, we also like to aim for all communities, including not just for Linux, but the developer developing different OS and hardware platforms. And then here is the roadmap. So since audio-reach is launched last year, Qualcomm engineer continued to work on adding more stuff onto to the open source project. We are hoping by Q3 of this year, we can upstream our kernel drivers support so that we can achieve the full upstream audio-rich Linux stack. At the same time, we're actively working on, as I mentioned, we're working on porting audio-reach to a non-Qualcomm SoC that has extensive DSP in the audio subsystems. So hopefully we can make some progress by end of Q3 this year, which is coming up in a few months. And then by end of this year, we are hoping to overhaul our development so that developing in public, so that whatever we are doing can be instantly seen by the outside developers, and so outside developer will be able to participate in code review discussions and all that. So that shows our commitment to grow this open source project to be a community-based project. Then for next year's. We are actively working on open sourcing audio-reach creators. As I mentioned today, even though there's a free version, but it's not open source, we are looking to rebrand QAC into audio-reach creators. At the same time, right now, QAC is written in C#, and using .NET framework. We are hoping to kind of re-architect to use a front-end language that's more cross-platforms, so that we'll be able to support Windows, Linux, and Mac OS. And we're also looking to support extensive DSPs running free RTOS, as previously we are looking to support on Zephyrs. Then toward end of next year, hopefully our engagement with MathWork will be would be completed so that we can start rolling out our vision of enabling the off-target development to on-target development visions. I think that's pretty much it. Thanks a lot for listening to these presentations, and please come to the demos.
Thank you very much. Okay, so Jan.
So thank you for the presentation. To develop an audio-rich engine plugin in C, is it going to work on every platform supported by audio-rich? Just a matter of recompiling it? Okay. And in the API of the process method, you can, so you have the input streams, the output streams, and for each stream you can specify a timestamp. So what happens if you have different timestamp in the different streams that you have to process? Do you need to realign them, or they are guaranteed to have all the same timestamp?
We have a framework module called sync module, which will synchronize those streams with different timestamp. Okay. So like for example, the echo cancellations, we have an EC reference, and also mic data. We use the sync module to synchronize those two streams.
And there is also length information, so you may have different lengths. You have to, this module takes care also of this case?
Different length. You mean like the
Yes.
frame size of algo? Like
no,
one
not the
algorithm?
different. In the stream, you have a buffer pointer that points to the samples, I guess.
Yes.
And then you have an indication of the size of this buffer. Are all the buffers of the same size, or?
I think the framework should be able to handle the size difference, but I'm more like the application subsystem side. So I probably have to take this as AI to ask the expert in working on the audio reach engine side.
Okay, sorry, it was very technical questions. Thank you.
Hi. I noticed you mentioned pulse audio, ALSA, and pipewire, but you didn't mention jack. Is that included?
This is definitely something we can look into. Like, I think we kind of gradually build up the adaptation based on our product requirement, and so far, our customers has been asking, starting with pulse audio, then we have pipewire. Obviously, ALSA has been the main API to access the drivers. So far, we haven't had any customer asking for jack, but this is something we definitely would be interested to add the support.
So I'm just curious, what was the kind of the motivation or the motivations within Qualcomm behind the movement from a proprietary system to open source?
Qualcomm is going through this developer-first transformations. So I don't know if you guys have noticed that a lot of Qualcomm developer has started doing a lot of kernel upstreaming. So that is definitely a priority for us to be more involved with the open source communities. And as Qualcomm wants to expand into more of a mass market products, more like IoTs, these are the type of product will require us to be more system ready. So then that kind of drives us to be more open source friendly.
You mentioned dynamic module loading here. And you also mentioned Zephyr. Are you actually able to dynamically load modules on Altos platforms?
I'm not sure about Zephyrs, but at least on Qualcomm platforms, the Hexagon DSP runs our own Quart proprietary OS, which has the dynamic loading capabilities. Having said that, even the audio reach engine needs to have the hook in order to utilize those dynamic loading capability. So we already enabled this on definitely for Hexagon DSP, and also when audio reach engine runs on ARM, the Linux comes with DL open support, so that we can also support dynamic loading, even when audio reach engine runs on ARM. But yeah, highly depend on the OS underneath audio reach engines.
Anyone more? I have just to conclude, just a couple of questions related. Sure. The first one, it wasn't clear to us what parts of the whole system would be open sourced. Is it everything? Like, is the engine going to be open sourced?
Pretty much everything will be open source, except the algorithm, because there are some algorithm we're still kind of monetizing. But we do have basic algorithms being open source today. Mm-hmm. You can actually find it in the audio reach project, GitHub project.
So the modules for the hardware, for the Qualcomm hardware, which you said that are pre-built, the source of those are going to be kept proprietary?
When you say hardware specific, are you talking about the driver that's configuring the...
I'm talking about those optimized DSP algorithms that you mentioned.
Algorithms.
Yeah.
Those are not necessary. What we do have, like for example, we have hardware resampler, like a hardware accelerated resampler. Those are, we're not open sourcing, but we do open source generic implementations.
Okay. And then just complement to this, do you envisage that you will also be sort of open to more like open source sort of development tools? Because math, as good as people might think, might like MATLAB and everything, it's not really within very much the open source world. So there are open source tools that are sort of Octave. Yeah, but also there's Python, all the Python scientific libraries and so on. And there is also Faust, would you envisage that you approach those more kind of the open source community to sort of strike partnerships and...
Sure, that's definitely something we can look into. It's just that, again, as I mentioned, we are aligning our roadmap to whatever is being planned on the product side.
Yeah.
Right. So far we haven't had the requirement to kind of look into those more open source friendly tools. But this is definitely something I will be interested. And if anyone here would like to kind of give us a pointers, I'll love to hear from them.
Great. Thank you very much. Right. So it's Fernando. Is Fernando presenting? Yeah. And so we're going to have a presentation by Fernando Lopez-Escarn from Karma. And he is going to talk about AVB for dummies or for Linux dummies.
Okay. We are talking about our experience with AVB on Linux. The dummies that are talking to you today are Fernando and Niels. We are systems administrators at Karma, Stanford University. And those sysadmin hammocks are not used enough. Karma is part of the Department of Music at Stanford, and we have a lot of spatialization systems, and because of the amount of speakers, we need to use network audio.
Yeah, so we have systems in our small concert hall called The Stage. That's a 56.8 system. We have an older system in our listening room, which is a full 3D 22.8 system. The studios have also multi-channel systems. And since the beginning, we have relied on Mod2 AVB interfaces, not because we loved the company, but because it was, at the time, the only affordable solution that was also not locked into exotic operating systems like Windows or Mac OS. So that's the listening room. That's the rack that currently controls it. All the blue displays are the Motus, and in the in the stage, so that's it. Still the listening room. Listening room. We also have.
Oh yeah. So we have an ongoing project creating wave field synthesis arrays. This one that you see is using three Dante integrated amps. They are super expensive. So if we want to extend this project, we need to find a much cheaper solution.
And that's the stage. And I believe at this point, I mean, there's tons of those Mod2 audio interfaces. There's approximately, I think, 11 audio interfaces talking to each other through AVB, controlled by a custom program that's running on a Linux computer. It's written in SuperCollider, uses some other, software like JConvolver, Worst Fonts. Thank you so much. And it does a lot of things. It aims to provide an easy-to-use interface for our users. So basically, you plug in your laptop into the system, you select the mode, and you can use it. So you don't need to know more about it. The problem with the Mod2 interfaces is they're sometimes dying. It's been many years, and here's an example. You can see the switching power supply control integrated circuit that developed a hole explosively. So the holy smoke that's inside that makes it work escaped, and it's dead. So we've been resurrecting some of them because I found an online supplier of power supplies, which is the first thing that apparently dies on these old things, which are now more than 10 years old. So the problem is that line of products is no longer made. So I watched over the past 2-3 years how they were becoming less and less available, and then until there's nothing left that you can buy, unless it's second-hand, used market. I believe that 2 days after we submitted our little write-up for LAC, in which we said, Mod2 AVB is dead. We don't know what the company is doing. They were not saying. 2 days afterwards, they announced the first new card on a new line, which so which is on a first test that we did. It sounds very good. It's supposed to be Milan compliant, and we'll talk about that. It can do 64 channels with the class compliant driver.
Like, they haven't announced yet that it will be Milan certified. But on Facebook, they do.
So, but anyway.
Yeah. So, yeah, we still need to find a solution, and we don't have this vendor lock-in anymore. We want something open source and open specs. We want to have direct AVB access, because if we, we could probably find a Dante solution where we could use wave field synthesis and use those PCIe interfaces with 1,000 channels, but it's expensive. ARM-E has some interfaces that you can get with AVB and with Dante, and the Dante interfaces are $200 more expensive. You have to pay for specific switches with AVB, but it's overall, I think it's still a cheaper option. And we need a smooth transition from the old motor AVBs to something new.
So for example, in the stage we have, as I said, 11 interfaces. They all have their own features, they have their own functionality, they're all connected together. We can't, and the place is used 24/7 all the year long for critical stuff. So we cannot do something like, okay, bring it down and say, okay, in 2 months we'll have the new system running. It has to be something that can be transitioned while it's running without interruption of service. So that further complicates things and makes it going to something other than AVB pretty much impossible. One thing we didn't talk about is why we need AVB and why is it, what is it we're using now if we're not using AVB to talk to the audio interfaces. And the fact is we're using USB. So the control computers are talking to one audio interface, for example, and that one is communicating audio to all the others using AVB, but the connection from the computer to the first line of attack in audio is USB, and that has been a recurring problem. It was impossible at the beginning, and there's some papers we published a long time ago. At the beginning, it was impossible. Mod2 issued a firmware upgrade that made it possible to use 64 channels over class-compliant drivers. That was a long time ago. A year later, they issued another upgrade that took that away. So suddenly we had a system we could not use. We found we could downgrade the firmware to the old version and get that back, but over the years, newer hardware that they sold of the same model couldn't be downgraded. I guess the internals changed, the hardware changed, and it was no longer, so we're kind of relying on very old cards that are dying, and we're trying to, do voodoo to keep them running. So that's kind of where we are now.
I want to talk a little bit about what AVB actually is. There's a base standard, 802.ABA. It's an open standard, so you don't have to pay for some license. The idea is to have a deterministic audio network. I remember when I worked at TU Berlin with Henrik, we had this distributed audio system with Raspberry Pis, and we used Jacktrip and OSC. And one time we had audio dropouts because one of the clients sent too many OSC messages, and this wouldn't happen in AVB. I get to why this is later. It guarantees a maximum latency of 2 milliseconds. Usually it's much lower. But that's not the only spec. For clocking, it uses GPTP. It's like a derived standard from PTP version 2. For this, usually you want to use hardware timestamping. And PTP is used for the clock, but you still need a media clock for synchronizing the devices. It's like a word clock.
Oh, were you going to say something about presentation time? Or?
You can.
Oh, okay, thank you. Yeah, there's two issues with timing inside AVB. One would be the synchronization of all the stuff that is on the same domain to a single wall clock, to the, I don't know, nanosecond level with luck, so that each one and every one of the nodes knows what the time is, the absolute time. And that is being used internally in AVB to say anyone that's sending packets, part of the packet is saying, oh, this packet has to be rendered at this exact time in the future, which is usually 2 milliseconds in the future. So there's all this time for the packet to get to the destination, and the destination has the same exact time, so it knows, okay, now is the time, and the audio samples go out. So all the sources and destinations are synchronized by this universal time code, which is handled by GPTP or Linux PTP. In addition to that, you need what's called a media clock, which is what's going to clock the samples out or in of A to D or D to A interfaces. That clock is not handled by GPT. It has to be derived from that somehow. And so you have to have that distinction in mind when you think about time within AVB. One is the presentation time, which is when the samples are going out or in, and the other one is the media clock, how often those samples are going to be sent out or received.
So for what I mentioned about that your control messages can't block your audio stream is usually one reason is that there's a stream reservation protocol. This means you reserve the bandwidth that you use for your audio or video. So this can't happen. That's 802.1 QAT, and this needs to be on the endpoints. Traffic shaping only needs to be implemented in the switches. So the endpoints usually are not that complicated in comparison to the switches. So the traffic shaping is for guaranteeing that the streams actually arrive in time.
So AVB needs custom Ethernet switches. So it will not work over regular switches. The switches have to support AVBs. That's the difference with other proprietary systems. This is what makes all these protocols that Niels was talking about, it's what makes it reliable. Other proprietary protocols, when lightly loaded, they work fine. When heavily loaded, they don't. And that can't happen by design in AVB. AVB is very complicated, but it's very complicated for a reason.
And it's not on that slide, but QAT and QAV are actually integrated in 802.1q 2011. So if you search for a switch, that should be enough. Then there's the transport protocol, and there was a difference. So Motu AVB interfaces used the old one from 2011, and it just reused the Firewire format for audio. In 2016, they introduced the AAC format and also the clock reference format. So there are small packets that are sent for the media clock synchronization. And Milan is using the new format.
This is just how to pack samples into packets.
The control protocol is everything that is audio configuration and discovery. So you just connect your interface to the network, and you shouldn't need to do a lot. So that controllers are separate devices in your network. The naming changed slightly to ATDEC because AVB actually became the time-sensitive network standard because industry was interested in those things. AVB changed over time, and there was a lot of incompatibility between devices. So ever new, those industry audio-video users, they created Milan to improve the interoperability between devices, and it's an AVB subset, protocol subset, but also a certification program. So if your devices are Milan certified, they should work with other Milan devices. So for PTP, the most common one is Linux PTP. There are others. There's one by Meta that is usually for more server stuff. And from Avenue, there's also a gPTP daemon. So the Linux PTP project, it depends on the hardware timestamping infrastructure that is already upstream in the Linux kernel. And on the right, you see that if you, with ETH tool, you can check for the timestamping support of your interface. So you should look out for hardware, those hardware capabilities. The filters are usually not necessary to have. The Avenue gPTP daemon, that uses a separate AVB kernel driver that is used for the AVB-capable Intel, i210, and other interfaces. So the PTP clock needs to be synchronized, usually with the system clock. That's not what Mode 2 by default does. It just starts at 0. You don't want to actually synchronize with 1970.
Well, yeah, unless you want to go back to the 70s, right? And then you do it this way.
So for AVDEC, there are a couple of AVDEC implementations. A big one is from L-Acoustics, and there's also the one that, an older one that is, that like the last change was 4 years ago. L-Acoustics AVDEC implementation is also used by Hive. It's AVB manager tool, similar to the Dante controller. And Christoph Kalmjan, who develops Hive, is also the author of the AVDEC library by L-Acoustics. And also, like, the simplified version of Hive is now the Milan manager. Yes.
Yeah, I wanted to say that if it's not clear, the AVDEC thing is a program that lets you see what's available, basically. And so you can list sources, list destinations, connect a source to a destination, look at what's available for a given node in the system. So you can poke and see what's around, either through the Hive, which is a GUI interface, or through command lines, more, like Linux-friendly, geek-friendly command line interfaces. And those are available as libraries with an API, so you could incorporate this into your own software.
Oh no, that's your point.
Yeah, maybe I'll keep going. So we've done some experimentation with the OpenAvenue software, which is a Git repository you can download. There's always something that you need to patch. Usually it's a one-liner and everything works. Well, works. I have experimented with the old Motu firmware, which is not Milan compatible, and it's not a complete implementation of AVB at all. So, but there's two main options that I found in this repository. One is called the AVTP pipeline, and the other one is live AVTP, which is newer. Both are contributions. AVTP pipeline is some company that did this and then released it. It's all not simple. AVTP pipeline implements the old scheme of packaging samples into Ethernet packets. So as such, it's compatible with the old Motus. LibATP talks the new protocol, but doesn't talk the old one. So what is it we did? If we go to the next one, I guess, or Yeah, this one only supports the new format, so it was not useful for my tests. I would have preferred to use this, but I was trying to avoid programming, right, and redoing things. So instead, the AVTP pipeline, which is actually, it has a set of shared libraries that implement different interfaces to audio files, to ALSA, to test signals. It's all driven through configuration files, actually. So there's a few examples that you can run with a configuration file, and that gets you up and running really fast. So I tweaked the examples, and I managed to get a stable connection to and from one of these old Mod2 interfaces, which is what we wanted. It says there is stable connection. Once it's running, it kept running for days, so that was very encouraging. Eventually, I found that media clock recovery was not implemented. So you get the samples in time to the other end of the connection, or you receive them perfectly. But if the clock rates of the devices are not in sync, you get problems. So, for example, sending from a computer to multiple audio streams would work for a while. Then you would get some little noises because it goes out of sync. Then it works for a while. Then you get little noises and so on and so forth. Because I'm transmitting at a rate that is slightly different than the rate at which the receiver is accepting samples, right? So buffers fill up and then jump to the beginning, fill up again, and so on and so forth. When receiving, it works because the receiving client does sample rate conversion, and then it all works. It needs some love in the sense of I need to recover from an incoming stream the media clock. And we haven't had time to actually do that. It's not rocket science to do it, but it needs to be done. Once I get an estimation with a running average or a PLL of this sample rate of any stream that is coming in to the computer, I can use that sample rate to send out, and everything will be synchronized. In a domain of AVB, everything is running in sync precisely. So once I get that, it should work.
But if you want to use also new devices, we would need AAF support, and that's not an AVTP pipeline. But the AVTP pipeline supports Jack. So that's also a plus. For the future, AVB and Pipewire is probably the best approach. Wim started this AVB module in Pipewire a couple of years ago. And when we tried it 2 years ago, we could connect motor interfaces, or our computer with a motor interface, and we produced beautiful crackling sounds. But it wasn't useful, and we didn't have the time to fix this problem. A couple of months ago, Simon Gapp and Alexandre Malki started to on implementing Milan in Pipewire. And they actually got a working audio connection, but there are still things that need to be fixed and worked on. Especially right now, most of the work is in implementing AVB DEC commands. But I hope that we find more people today that actually want to work on this, and maybe we have Milan certified Pipewire AVB implementation in the future. So please reach out to that guy. That guy also started the AVB Academy. It's a website about AVB and Milan. So if you want to learn more about AVB from the user side, but also from like the protocol side, you can look there. And there's also help wanted. So if you find something that's not clear or you just want to extend, please reach out.
Yeah, I may want to add one little thing, which is, it is a complex spec, but keep reading it. So the first time, in my case, I understood pretty much nothing. And the next time I read it, I said, oh, this makes sense. And look out for, there are several good tutorials online that go through the whole process. At the end of the road, after you read it several times, it makes sense and you're able to understand it. So don't get put off if at first you can't figure it out, because it's many interconnected parts and subsystems that talk to each other. All together, they make a pretty good system.
All right, thank you very much. We have 3 minutes. So it'll have to be quick questions. So there are 3, 4, that's it. So it's on that line, so we can start from that side there, and then we'll come to this side.
So, as somebody who usually does multi-channel music with very low threshold setups, is there any resources how I could benefit from AVB, like as someone who usually does DIY multi-channel setups and things that are easily available? Because I always found it like, I looked into it and I never really found the entry point, let's say, so how to actually use it for things.
You mean how to use AVB, or?
Like if I go to a venue and they tell me, you can play here, but you can plug in using AVB, what would be my, my resources there as a Linux musician?
I mean, I would say we are not there yet, except maybe in specific situations. If you are used to GStreamer, you might be lucky. Okay. But I don't think it's a plug-and-play situation right now. Okay. I mean, that's what we work on.
Okay.
I think it's really close because, as you saw, most of the protocols that we need are actually already implemented. And like for the, I did mention the AVDEC library by L Acoustics doesn't implement the endpoint part of AVDEC. So that needs to be implemented in Pipewire directly to make this a seamless thing.
Yeah, hi. Thank you very much for this great presentation. I want to point out one thing that was not clear for me, at least from your presentation. That's the latency issue. So the presentation time offset in AVB can be set to up to 2 milliseconds. It's not fixed to 2 milliseconds because for some historical reasons, this is sticking with people's minds. So AVB is not 2 milliseconds, it's up to 2 milliseconds, and that's a bounded latency, so it's guaranteed to that value.
And how much, how low it can go, it depends on the number of hops, Ethernet switch hops that you have. In the software I was working with, AVTP pipeline, this presentation time limit is just a number that you put in a configuration file.
Hey, thanks for the presentation. And I've been thinking about AVB2, and I know it worked when I was at this stage, so it's just working. It's just working. But so I've been doing like more like trying to work with AS67 and unfortunately Dante. But there's a lot of hardware that does Dante. So, but you, I mean, like you basically run analog connections from all the AVB interfaces to your loudspeakers, right? So that means you don't run a lot of network cables, right?
No.
So you could switch systems, right?
In theory,
yeah.
In practice, you mean switch, for example, from AVB to something else?
Yeah.
It's possible. It's not impossible. It would be very hard. For example, if I were to migrate, I would, for example, replace the interfaces that drive the speakers first, so that I can test that part, and everything else stays the same. It's just the streams go somewhere else.
Is it
And
64 channel? How many is it?
No, I mean the...
No, how many channels do you have now, like as an analog? How many loudspeakers?
64.
64.
64 total. And those are handled by, I mean, we cannot go into the detail. It's a very complex system.
Okay.
So it would be very hard to, I mean, if I were to transition at once in one thing, we would have to basically have two parallel systems running. And then at some point switch. And if it doesn't work, what? We go back to the old one. We always have to have a way to go back. We cannot do something that we cannot go back to the previous stage that was working. And that makes it very complicated.
AES67 compatibility is also in the AVB specs now. But I don't know any details. So maybe it's like transition option to go from AES67 to AVB. I don't know.
I have a new bike question. How do you currently feed the system from jack or whatever you're using on the stage to play it out? Because I think there's something missing.
Yeah. We're going through a USB.
Okay.
So we're running jack, we're running Super Collider, we're running J-Convolver. Everything goes out 64 channels over USB. And that's what we hate. And it's a source of tons of problems. After that, everything is AVB. Until you get to a point where there's analog audio coming in or analog audio coming out or another USB connection. So for example, a user comes with a laptop and it connects to one of the Motu interfaces, which is different from the one that's actually controlling the system.
I see. And so in the new Pipewire implementation, it will be everything in user space. Like there will be no kernel driver. The kernel driver will be the Ethernet driver. There will be no ALSA interface.
You will, I'm not sure. You will need something in the kernel to do the hardware timestamping and all that. And maybe if I do this and I don't make a mistake and fall.
You can take this offline later.
Yeah, okay, great.
We ran out of... Yeah.
So I'm sorry we're out of time.
Yeah.
Thank you very much.
No, thank you, everyone.
I got the microphone here. So we have our final speaker for this session, and from one type of bridging now to a different type of bridging. So we have bridging, musical gesture, and computational representation, designing gesture composition framework, Markidis Marco Matteo. Thank you very much.
Hi everyone, my name is Marco Matteo Markidis, and today I would present my work that the title is quite long, but is indeed Bridging Musical Gesture and Compositional Representation, Designing Gesture Composition Framework. So the arc will be quite straightforward. So basically I will just, before to start, I will just introduce myself and give you some definition. Then I would talk a little bit about the current landscape, and then I will introduce you the framework, and I will give you some analysis, some quantitative analysis I did on it. So who am I? Basically, I am an independent researcher and a composer. I just list a couple of interests of mine. Probably I actually am more interested in compositional aspect than in coding, but that's it. I mean, what I'm really, and what I want to say with this slide is that indeed the gesture composition framework emerged from my practical compositional needs. So effectively, at a certain point, I just was stuck with the last piece of mine, and I just say, okay, I need to write some code from scratch, and I wrote it. So effectively, this framework born was from my compositional needs. And also I took the liberty to to mention a statement from McCartney from one of the Super Collider article that basically states that a computer music language should provide a set of abstraction that makes expressing composition and signal processing idea as easy and direct as possible, because effectively that was indeed one of my designing goal. Before to start, I would like to give you some definition, and because just to be clear, effectively, indeed, when I will refer to gesture, I will refer to the smallest meaningful unit of musical expression from a compositional perspective. So there are a lot of literature about what is a gesture, and you can find it quite easily. However, what I would mention is that the definition that I use is more from a compositional point of view. It is not related to some physical aspects, to motion or this kind of thing. It's more about what can be from a compositional perspective. And even composition framework. So effectively, my emphasis was about the organization and the structural representation of music idea, just to provide abstraction for expressing temporal relationship musically intent. So what is the scope of the framework was and is just to have a computer-based composition framework with a gesture-centric organization, which may have various output modality. So here the bracket, because now all the tests that I done are related to direct audio synthesis. However, was one of my design choice to think a system such that I can have also some output that, for example, I can use for an instrument, or I can write, just to say, traditional music. So the opening question was indeed, what if composers could work directly with musical gesture as computational primitive? So actually, a composer, at least in my opinion, if want to write a gesture, should translate it, okay? Should translate it in a text-based language or in a visual programming languages, or in other ways. So what I mean is actually a composer needs to translate its own musical idea in something else, okay? And what is missing is effectively a framework where a gesture is treated as a first-class computational entity. So what I feel is that effectively in all the current computer-based composition approach is missing an abstraction, a gesture given as an abstraction. So basically there is an implementation gap in my mind, and indeed there is no temporal abstraction. And plus, I saw some, just to say, bad feelings I had in my life. One is about the error. So effectively, usually when I have an error, is something that I get it directly during a listening session. So I just patch, I just do something, then I start to listen, and at a certain point, loudspeaker start doing bad things. So everything is postponed, just to say, to the last minute, and also the complexity grows in a non-linear way. So effectively, it may be possible that something could be easily patched, and if you want to just add something else, the complexity grows in an unexpected way. So just to quote Paul Lansky, the result is that indeed the composer must become fluent in both the language of the music and in the language of a computer. So this creates, as Lansky said, a dual cognitive load for the composer. So I just introduced you gesture composition framework. Basically, my goal was to introduce a framework in which the gesture is given as a primitive, this, in my opinion, should give a more direct representation of musical thinking in code. Then I try to develop it using a type safety approach. So I use a C++ concept, and I try to have something that have what I call complexity invariance. So something in which a composer can have, just to say, the same gesture with one evolution, one pattern evolution, another pattern evolution without complexity scaling, and also just to have something related to temporal abstraction. So I try to introduce some way in which the temporal evolution can be easily used, or the system give you by default some facilities while using it. So I introduce something about patterns, or indeed parameter evolution, or trajectory in the space. So what is in my idea a gesture? It is simply a compositional entity which have a temporal accent, so it has a start time and a duration, a parameter evolution, so that can be static, linear, quadratic, or custom, and we will see it. It has a link to an instrument processing, but actually it is the sound system, the sound synthesis processing, or it can be also some different output modality. Optionally, can have a pattern-based temporal abstractor, or also a spatial trajectory. So this is, just to say, the overall architecture. So without knowing too much with this detail, my main goal was, and even from the design perspective, where I start was from gesture builder. So I start from the bottom, from to say, okay, as a composer, how I want to write a gesture, and then I design everything else. So I start from that just to arrive to the audio rendering. So even my design was based on this idea, just to think, okay, as a composer, how I want to write music, how I want to write a gesture, and then I chain all the rest, basically. And I also introduce what I call conceptual mapping ratio. So I just try to give a quantitative analysis to what I wrote. And indeed, I introduce a metric that I call the conceptual mapping ratio, that is basically the ratio between a musical concept and the implementation element. So with musical concept, I mean every distinct musical idea a composer can insert in a gesture. And the implementation element is effectively how many method code constraint, or whatever the composer should implement to have that given gesture. And this result that effectively a higher CMR is a more efficient expression for musical idea. So here's just some code. So as I mentioned, from where I start, from the gesture builder, I use a builder pattern, and here you can see some idea. So basically, I just use a method chaining with set tracking. So effectively, we have, as I mentioned, a gesture is an entity with a starting time, a duration, and temporal evolution about parameters, and any eventual optional pattern. So effectively, this is the core from which I start. And some benefit that I would mention is that the state tracking, in my opinion, it's quite interesting. So effectively, we will see later, however, if you try to construct a gesture without basically or the starting or the lasting or so far so on, the code will result in an exception. So effectively, this was, in my idea, one way to help the composer to write the code, to implement in a correct way the thing. And so this is my first gesture. So effectively, we can see from here that we have a gesture that links to, in this case, to an instrument that I just call Synosc from the tradition. That is just simply a sinusoidal generator. And roughly speaking, this creates a gesture that starts in a timeline at 0 point. It stands for 2 seconds in this case. And it explicits the two parameters, one that I call amplitude, that are related to Synosc, and the second one to the frequency. And then we had the create method that effectively create the gesture itself. So in this case, it was, in my opinion, a good starting point, because effectively, with 6 implementation elements that I just tell you, I managed to express a gesture with, in my opinion, 5 musical concepts, because effectively I have, you can have a look at the paper, however, I have a link to the instrument, I have a starting point, I have a duration, and I have the 2 parameters evolution. So effectively, this gives me a ratio that is 5/6, that indeed is a reasonable starting point for my analysis. And then I just try to add some parameter evolution. So effectively, in the previous case, let me come back. So in the previous case, the amplitude start, so for instance, the frequency start at 440. So, and in this case, we have a constant frequency, so we have no evolution in time. While on the other case, so in this case, effectively, we are expressing an evolution, a temporal evolution that starts from 440 and go up to 880 in a quadratic way. So effectively, we have a frequency sweep, okay? And also we have something similar also about the amplitude. We have a crescendo in the amplitude that starts from 0.5 in RMS and go up to 1. So effectively, in this case, the fact that I'm expressing a temporal evolution of my parameter does not introduce any new complexity, because the number of basically the number of code construct introducing is nothing new, because effectively even before we have indeed a temporal evolution that is static. In this case we add it, but we have no significant shift. Then basically each instrument you want to write basically derives from this concept that I call processable. Okay, so effectively a processable and also an audio type that extend processable is indeed support C++20 concept. So this give us an enforcement about the type safety, because effectively at compile time we can understand if we are providing all the necessary elements for our processable. I also spent some time to understand if effectively the domain-specific language that I'm developing was quite fluent, and I tried to have a code that reads in a more natural way as possible. Indeed, I tried to effectively to express the intent, the musical intent of the code in a simple way. Then, this is one additional feature, as I explained before, that is called pattern. So in this case, this is an abstraction of the language. Basically, this code, you can add this code basically to a gesture. In this case, what will happen is that basically we create a pattern. You can see basically at line 5, in which you have a pair of sound and silence, such that there is a transformation basically such that you can have a look at the full code from from the repo. However, the idea is this one, that effectively, if you want to obtain a temporal structure like in which the silent progressively disappear, this could be difficult to do usually. Well, in this case, the idea could be to have a pattern that repeat and while repeating as a transformation. So just to apply a transformation, in this case, to a pair of sound and silence. Yep. About the pattern evolution, one additional point is the code, the framework provide you a constant evolution, a linear evolution, quadratic evolution, but also one benefit that I see is that you can use directly lambda, basically. You can use a lambda function to create custom pattern. In this way, even if it is not coded, there is no an evolution type that I already provide to you. You can easily do it by yourself, just writing a lambda function. And also, you can derive the duration of a gesture. If you are using a pattern, you can derive the duration from a gesture while using the ending condition on it. So if you have a look of line 9, in this case, what I say is continue to do this gesture until I will reach an ending condition. So in this case, I'm not saying this gesture will stand for I don't know how much, but I will say derive it automatically from when I will finish this thing. Yeah. Error handling, basically, as I mentioned before, I'm using state tracking to understand if I'm providing all the necessary elements for the gesture creation. So in this case, for instance, in the first case, I am missing to provide the frequency for the SYNOSC generator. Okay, so effectively, when I will try to build it, I will obtain from the constructor. Basically, I will have an exception because I do not provide the necessary elements to construct the gesture. And in second case, I'm providing a negative frequency. So if we have a look of the SYNOSC, I just defined that the frequency for a SYNOSC cannot be negative. So in this case, what happened is that effectively I will have an exception for it because I'm providing a negative frequency. Yeah, I also, at the time of the paper, the framework was only for a mono channel, and in the last period I also work on to provide a special implementation. So this is my actual idea, basically to have a special configuration. In this case, I'm just working with a 4-channel in which I define the setup, and I give proper name to the loudspeaker. And in this case, the method spacing acts as a napping, so effectively I can define the trajectory in this way using a linear evolution. So some result. So I managed to attain a quite definitely high conceptual mapping ratio for the gesture I analyzed. And also I managed to attain a quite comprehensive parameter validation and runtime error detection. Indeed, I have tested quite extensively. I also managed to obtain some key design achievement. Basically, one is to pass from a simple gesture to a complex gesture in a quite easy way, and also to have to understand that effectively the abstraction are working as I expect. Indeed, when I analyze an example with an abstraction, I have an higher CMR. And last but not least, I believe also that this can give to the framework a predictable learning curve, because effectively the fact that I have the fact that I manage to add complexity without changing, just to say, too much the language means that a new user could be easier for a new user to understand the language feature. Last but not least, as I mentioned at the beginning, gesture composition framework was born from a peace of mind. And one of my next plan is effectively to reimplement section of this piece using this tool. And one of my goal is to understand if how much the language change the writing of the piece. Indeed, I'm interested to understand if it acts as just to say in a transparent way, or effectively if it acts as a mediator. Some future direction, just to mention a couple of them. On the left, some technical aspects. So actually, there is no real-time support. So everything is just to what the framework does is to create a WAV file. Okay. So effectively, that was indeed my original goal. So I want to understand if it's possible to do something on that. And to understand how, if I can give transformation to gesture. So effectively, if starting from a gesture, I can transform it, obtain a different gesture. So effectively, if you think to a theme with variation, I can have something like an initial gesture and then vary it to obtain music. While on the contrary about just to say integration ecosystem, if effectively I can add more output modalities or can use more pattern transformation, or indeed if effectively I can understand how to communicate with other language. Because actually I do not have, and it was not my goal to have a lot of processable, a lot of audio type. So effectively I was more involved in the design of the software. So I also open to understand if I can create communication with other language that already offer this kind of features. And that's it. Yeah, thank you.
Thank you very much.
Yeah. Of course, I forget to mention that the repo is there. There is my contact, and all the code is there, and I open to collaboration. You can, yeah.
Okay, questions? Jan?
How can you compose, so you mentioned that you can compose gestures, which is obviously a very interesting idea, but do you have operations to compose gestures together? For example, in one of the examples, you give a gesture that was involved in two parameters, the amplitude and the frequency of an oscillator, but you can imagine also to have a gesture only on the amplitude, for example, of this oscillator, another only on the frequency, and have an operation to combine them. So do you have this kind of operation, or is it interesting from your point of view?
No, I don't have, and no, it's not so interesting in my perspective, because one of my goals was indeed to have, just to say, an atomic unit. Just to say, if a sinusoidal generator needs an amplitude and a frequency, I would give them to it together, because effectively, my analogy is, if I write for a violin, usually I would give to it all the parameters that are needed to play something. So in this sense, I was more forced to do it, to pack things together just to have a unit. However, what you can do, if you are interested, is effectively you can have, if you think you will have a complex trajectory, complex pattern evolution, you can effectively have them separately and use them as lambda inside the same gesture. So in that case, the result will be just to have one gesture, but maybe the code can be split over different parts of your project.
Okay, so I'm looking at that from the background of the live coding idea and of the live coding scene where I'm coming from. But so when you talk about gestures, you're talking about something that you're looking for code to implement, or are you looking at the code itself as a gesture and then writing the code? Because that's what we often do in the live coding scene, that writing the code in itself and the code itself is a kind of gesture. Is that something that you look at a certain angle you look at it from, or are you?
Just let me, so basically you're asking me if I am interested in, so if I consider that the code itself is the gesture.
Yes.
That is the question. Okay, no, not in my opinion. Or at least what I do in my daily life to compose. I mean, as for sure you will know there are, I mean, it's an open topic discussion about if the code can be the score itself. So I'm referring to Tor Magnusson works or this kind of paper. Not in my idea, because effectively I'm more interested to work with score. So effectively I have score with me, and usually I'm more involved in writing score and then to translate them. So that is, but it, of course, is my approach, and I am indeed, you know, it's a very interesting field. Indeed, if you remember, I also quote something like that in my interest about to understand the difference, just to say, between notational and representational aspect in computer music, just to say, because effectively the line it can be tricky, and if you tell me, okay, but do you consider that your code exactly your gesture, I can see your point, even if, to be honest, I'm not composing that way. Okay.
So thank you to the speakers of this session. Thanks to Victor for chairing it. So now we're going to have a coffee break with demos. The demos will take place here in the theater. They're going to be on the 4 corners of the square. So one here, one here, one here, and one here. Feel free to go get coffee upstairs, to come back here. You know, and we're going to do this for an hour, and this will be followed by a workshop by Robin, yeah, which will start in basically an hour. So thank you.